this is the recording attempt number 3. And my screen also went to sleep, so okay. All right, back in business. So just to state what this balance means, okay? So we're gonna do in a shell, which is really small volume of fluid, rate at which momentum enters minus, so basically we're going to look at the rate of momentum coming in minus rate of momentum coming out or going out. Plus any, so this is momentum coming in and out. We might have actually some body forces acting on this volume, the entire volume. So when I'm looking at things going in and out, I'm looking at the boundaries of my shell, right? So what's coming in and out through the boundaries, literally through the door in and out. But then there might be simply some body forces acting equally on all portions of my shell. Gravity is one such thing. So body forces acting on the element or shell. So that has to be equal to rate of any accumulation inside, right? In this shell, and this is going to be something that is 0 for steady state. So when I say momentum, I mean combined. So this combined momentum has the molecular component, which we call P, and it has the convective component, that's that rho VB. Okay, so this is combined momentum. And this combined is precisely that V is P delta plus tau plus rho VB. All right, so I'm gonna do a new, I want to do a drawing and start solving, so I'm gonna start a new page here. Save. Open. Okay. So let's do a problem. This problem is our first example and the simplest one. It is the steady laminar flow of a Newtonian fluid down a gently sloped wall. Okay. So we're going to call this actually thin film example. So the flow is steady and laminar. And this is from chapter 2.1 in BSL. Fluid is Newtonian and incompressible. And geometry is down a gently sloped wall. So let's draw this geometry. And what I'm actually drawing is not gently sloped, but I have to exaggerate. Gently sloped is this, okay? But good luck seeing anything if I draw it that way, okay? And I'm going to call this angle beta. The length here is L. And this wall is 3D, though we're not going to be solving it in 3D because I'm assuming symmetry. There's width W here. I'm in gravity is acting downwards. And I'm imagining a thin film, so basically there's film here of fluid. Okay. And the thickness here is delta. So first things first, I'm going to choose a coordinate system. And I'm going to align mine with the slopes. What else? So basically, I'm going to do something like this. I'm going to redraw that coordinate system. Right here. So I'm going to call this direction Z, this one X, and the one into the paper is Y. And that one I'm going to completely ignore when solving the problem. And that's because however I slice this film in Y direction, right, I expect to see the same picture. So I'm going to solve for that, right? So I'm assuming everything is the same into the wall. And so I have a two-dimensional problem. Yes?
So just confirm that the z-axis and the y-axis are aligned with the...
Everything is aligned with the slope, yes. Just like, so basically red here is red here.
No, I'm saying that z-axis and the y-axis are aligned with the slope and the other...
So x is going down.
Yeah.
Yes. So x is going orthogonal to this slope here. And z is going down the slope, right? Now, what is my shell, this shell that I'm talking about? And I'm now here within the fluid. It's just that there's no space here to draw. My shell is something like this. So I'm imagining a little shell of fluid, okay, inside this film. Okay. And that shell starts at, it goes from z to z plus delta z, and from x to x plus delta x. So that is my shell. So again, shell is in coordinate system. And right now we are in Cartesian coordinate system, but soon enough we're going to be in cylindrical, right? We gotta solve for flow in tubes. Look at those tubes over there. Okay? Cannot avoid tubes. Everybody's like, what are those? Logging tools, artificial lift tools, all kinds of tools. Okay? So in this coordinate system, I got to balance momentum. And momentum, we said, was phi, my infamous tensor. But this was a tensor, right? So this is the combined tensor flux. So which components of this tensor are actually relevant in this thing? So anything that has to do with y, I'm going to ignore, right? So I'm ignoring y direction. So the ones that we actually have that are doing anything are phi xx, phi xz, phi zx, and phi zz. Everybody agrees? So relevant here. Y ignored, because everything is same in that direction. So momentum has a direction, and momentum transfer has a direction. So we have to actually balance direction by direction. And whenever I have this flow that is aligned by flow, that is aligned along a certain direction, that's the first direction to actually do my balance in. Right? So we're going to do this direction by direction. So in z direction, the momentum components, or the ones that are balancing z momentum, are which ones of these two? So remember that tau yx was x momentum transferred in y direction. So tau xz would be z momentum in x direction, right? So anything that has this z at the end is what we're looking for, right? So that's why z momentum going in different other directions, right? So the ones that I'm balancing first are phi xz and phi zz. So it's z momentum. So if I'm looking at this side over here, gonna imagine if anything is coming inside this, into this volume, it's coming through this way, right? And it can leave here. And this would be, so I'm transferring z momentum, but this side here is x direction side, right? So this would be phi xz coming in. Yes? Because it's transfer across x direction. And this is, I'm going to call it evaluated at x, which is this location right here. And here on the bottom, I would have phi xz evaluated at x plus delta x. So there's just notation. And when I have this z side, right, or it's a coordinate plane, it's that, if I'm looking at the z momentum that is coming across z plane, that's phi zz. Yes? So I'm gonna choose a slightly different. So here, I'm gonna have phi zz, and here it's evaluated at z plus delta z, and here it's evaluated at z. Now the reason for this notation, when I write down phi zz at z, my phi zz is a function of x, y, z. I don't want to write all of that, right? So this is evaluated at z, keeping x and y constant. And in this case, we're ignoring y, so keeping x constant, right? And if I evaluate, again, this phi z evaluated at z plus delta z, keeping the other direction constant, I just don't want to write it down. So this is the reason to write it this way, okay? So it's really phi z of x z, but this is the relevant thing that I'm evaluating right now, right? And this one is kept constant. Okay, so that's the notation. So what is my balance? Okay. It's quite literally, so there's momentum transfer, and momentum transfer, the way we are defining, it's actually per unit area, right? And we're actually looking at the component that is orthogonal, so all of this component is going to come in, okay, because it's coming in orthogonally to the side. If it was actually coming in at an angle, I would actually have to do a dot product and project some of it, right? So when I'm looking at this component coming in, so I literally just take the value of it, phi xz, and times the area of that side, right? That's what's coming in actual amount. Because my phi, as defined, is per area, right? So it's normalized. So in actually to get the amount coming in, or the rate coming in, I take phi xz. Let me actually do correct coloring here. I'm back at this phi xz side, so I'm going to use black. Phi xz evaluated at x times the area of that side is what actually flows in, and area of that side is delta z times this w. I'm going to put w in there. It's going to just, I'm going to cancel it anyway, but like I'm going to write it in because I know that phi is in per area, so I want to keep that. Okay. So this is my area of the side. Okay. And then what's coming out on the other end that is parallel to it is phi xz evaluated at x plus delta x times the area of that side is the same. Thanks to the Cartesian coordinate system, areas are the same. In a cylindrical coordinate system, they're not. And I have a cylindrical shell. My area keeps increasing as I'm moving away from the center. This makes things slightly easier to solve, okay? So Cartesian is good. Okay. And then I'm going to add in blue the rest of the balance. That's my phi zz evaluated at z. The area of this side is what? Delta x times also this w that I'm going to. And minus phi zz evaluated as z plus delta z, delta xw as well.
So just to make sure, the area that you're specifying is the area of the plane that is perpendicular to the direction.
Around this shell, so I'm looking at the little box of volume, so it's area of that side of that box. Okay. Because I'm actually trying to get the actual amount, right? Otherwise, the tensor is per area, so it's normalized. It's not telling me the actual amount. What I actually did here, I did a surface integral of this tensor acting on these surfaces on the side around this box. Okay, so I collected all of the components of that. Okay. So if you remember surface integrals from your multivariate calculus, that's what we actually evaluated right here. Cool. So now in that shell balance, this is basically my z momentum. Okay. Now I also need to do z direction forces acting on the system, and we have gravity, right? It's just that I have to project gravity down this slope. So basically I'm going to have the density of the fluid, right, times the and this projected gravity G I'm going to project, and a volume of the element, right? So it's going to be plus rho G cosine beta will project on the Z direction, and times the volume is delta X delta Z times W. So this is my body force. Should have done it in a different color. Let me do it in a different color. Obnoxious green. No, red. Rho G cosine beta. So all of that, that's the only body force I have here. Easy peasy. All of that at steady state has to be equal to 0. The most of our work is done posing the problem. Now it's cleaning it up. All right. First thing that I'm going to do, I'm obviously going to divide by W. And not only that, I'm actually going to not only divide by W, but by delta X, delta Z as well. So divide by volume of the shell. Everybody done with this? I'm going to the new piece of paper. Piece of screen, new piece of screen. So I had that phi xz evaluated at x times w delta z. When I divide that by w delta x delta z, I'm actually dividing by delta x, right? And I had minus phi xz at the other end, right? So basically what I have here, oops. And then plus phi zz evaluated at z minus phi zz evaluated at z plus delta z. Sorry about that. Started writing delta z. And then what's left of the body force is just rho density of it. This is body force density. So this is the part where I'm going to let this shell shrink around the point. And I'm working this for any kind of point in the fluid. So this is valid throughout the fluid. So I'm going to let delta x go to 0 and delta z go to 0. So my shell shrinks. And this is how we arrive at differential equations, really, in this limit. So when I look at this, my z in this particular case is kept constant, right? And because I'm evaluated at x and x plus delta x. And I have this, if I think about it, as negative phi of x plus delta x minus phi of x divided by delta x, and then I take limit when delta x goes to 0. What is that definition of? Derivative, partial derivative, right? Z is kept constant. So this is basically minus partial xz with respect to x. By definition, textbook definition of partial derivative. And then here it's going to be negative also. So again, normally in a derivative I would have phi zz at z plus delta z minus the other one. So that's why I'm taking negative here. This is partial zz, partial z. And this is a constant as far as delta x and delta z go. So I'm just going to, nothing happens in the limit. This is my Z momentum balance in differential form. It's valid at any inner point of the fluid. We derive this. Is this specific to any particular type of fluid? This is general, okay? So any fluid I had here, this would be valid. Question is, do I know what phi is? Okay. Do I have a formulation for phi? So this is general for any fluid. And this is where my thing just stops writing because it just does. I can write with this. Okay, it's general for any fluids. We have like 5 minutes left. I can narrate. Okay. Now, what is phi xz? You actually keep writing. What is phi xz? Actually, I can do this. So my phi xz, for some reason my pen doesn't want to write right now. It is, my phi is combined momentum, right? Which components does it have? Pressure, does it have pressure in xz? No, so that part is 0. I have tau xz. Plus oh, not terrible. Okay. And then my phi zz, it does have a pressure component, right? ZZ direction. And it's just P times 1, right? Plus tau ZZ plus rho VZ VZ. So pressure, I have pressure because ZZ is normal, acting normal to that surface. XZ is shearing. Okay. So the action of that force, if you think about the force view of momentum, is shear in XZ. And in ZZ, it's normal. It's still transferring across the surface, but it's shearing force that transfers across the surface. Cool. So now I actually have to go, so this is my, I know what tau, my tau will actually have the form of the Newtonian fluid because I'm assuming this is a Newtonian fluid. But before I split that apart, let's assume, what did we assume about velocity? So my velocity, this is a very thin, slow laminar flow down the slope, okay? I'm going to assume that my only velocity that is alive is Vz, and that I actually don't have anything coming down. So that's a very actually almost horizontal slope, okay? So my Vz is the only non-zero component of the velocity. And frankly, if you don't come to that assumption, you won't be able to analytically solve. So for the most part, this is going to be our assumption. Okay? Find the dominant, so there's only is non-zero. And my Vx is 0. So those are assumptions. Is it completely true? No, but it's close enough. And then that Vz depends on which direction?
Next.
Only on X. So I'm going to assume that all of the layers are kind of moving in unison as far as the direction goes. So I don't have any acceleration down this slope because the slope is nearly horizontal, right? So wherever I see in Z direction, I'm going to see the same velocity. So this is only dependence. Again, unless you assume in most of these partial differential equations, unless you have to assume that you depend only on one direction, otherwise it's extremely difficult to solve the coupled PDE. Okay? So for the most part, you have to simplify it down to having only one velocity direction active and working depending only on one other direction as far as XYZ goes. All right, we're going to complete this on Monday.